All right, welcome to lesson number 7. Probably put lesson 7 and lesson 8 together today. We'll do scatter plots and linear correlation all as one. You've done scatter plots in grade 9, y equals mx plus b. There's a lot that's going to be familiar to you, but we're going to take it maybe one step further, and we'll really try and understand what data means when you put two sets of data together. We've been doing one variable data. So what that means is you've had one set, you've been finding the mean, the mode, the median. Height of a team is a good example. It's really easy to calculate, but we don't usually work in single variable data. Oftentimes we have multivariable data where we've got to analyze the different sets together. So an example would be height of a team versus the number of points scored. If you think about basketball, generally speaking, the taller your team, probably the more points you're going to score, more rebounds, etc. But we've got to justify that somehow using the tools we're going to learn today, that there is actually a correlation between the two variables. So the question you want to ask yourself is, well, when does it actually matter? And what we say in stats is that if a change in one set of data causes a predictable change in the other, we say it's correlated. So if you were to continuously increase the height of your team, you would expect to score more points. If that happens, then we can say that there's a correlation between the data. And what we usually try and do is study the independent variable and what the effect is on the dependent variable. Two other ways to talk about independent and dependent is the explanatory and the response. So what happens to the response variable when you change the explanatory variable? In grade 9 you learned about correlation, and this should be a review. You can have positive correlation, negative correlation, or zero correlation. And depending on how much change there is with that dependent variable, you'll either have a perfect correlation, strong, moderate, or weak. And you've seen these type of graphs before. So for example, this is a perfectly correlated graph. So every time the y value goes up by 1, the x goes up by 1, and it just becomes a step pattern all the way through. You can see here these R values. We're going to focus on this in a second, but just keep them in mind as we go through. You can see this is obviously positively correlated. It's going up and to the right, and it does have a strong positive correlation. The data points are pretty close together. If you were to draw a line of best fit, you can see the data points fit pretty close to that line. Whereas this one, you can see that there is zero correlation. They are all over the place. And then it flips around and just does the opposite to the negative. So for example, this set of data here is moderately correlated because the data points are not quite as close together as, say, this one is. And you can see the values for R change. This one's a good example of the effect of an outlier. You can see there's a data point way up here that doesn't seem to fit the trend of the data. And instead of being a perfect 1, like up here where the positive correlation is, it decreases to a 0.71. So we're going to talk about outliers, and I want you to remember that change. It's a 0.3 change, and that's pretty significant as we go through the rest of this unit. Here's a pretty good graphic that shows you the scale. If you have a perfectly negative correlation, so for example this graph here, you can have a -1 R value. So the scale ranges from -1 to +1. Perfectly strong positive is 1, perfectly strong negative is -1, and then there are values in between. You can see here between -0.1 and +0.1, there's no correlation or an R value of 0. Just indicates that there's nothing going on between the variables that would cause correlation. The question is, how do you actually calculate these R values? Because it's one thing for us to state that we believe it has positive, weak, positive, strong, negative, strong, whatever, but we've got to be able to prove it. So here's the formula we're going to use to calculate R values. Looks a little bit cumbersome. It is. There's no doubt in my mind that this will challenge you, but the good news is that you will never have to calculate the correlation value or the R value by hand. So I'm going to walk you through two different ways to correlate it, or sorry, to calculate it. First is going to be using a spreadsheet. The second will be using your TI-83 calculator.